Good morning. Today we will continue about topic the classification of crystals. The theme of lection, the crystallograph symmetry classes and Bravais lattice. Class or type of crystal symmetry is called a complete set of symmetry operation of this class. The further of division is the set of symmetry operations characteristic for a given polyhedron. All varieties of crystal symmetries of polyhedron and their physical properties are described by 32 classes of symmetry. Each of the 32 classes of symmetry is denoted by a special character. All characters are based on the theorems of the combination of symmetry operation, and each symmetry class has its own designation. For example, 2mm, 3m, 6 divided m, etc. What is it, the symmetry formula? The formula of symmetry is all the elements of symmetry recorded in a succession. In the first place, there are usually written symmetry axes from highest to the lowest. In the second place, the plane is of symmetry, then the center of symmetry. So the symmetry formula itself does not carry any information. But you can see a full set of element of symmetry if you write correctly the formula of symmetry of this crystal. For example, the formula of symmetry of the cube is 3 axes of 4 order, 4 axes of third order, 6 axes of second order, and the 9 plane of symmetry and center of symmetry. However, the symmetry formula itself doesn't carry any information. To decipher it, we must take into account the theorem of the combination of symmetry operation. There are a lot of theory of symmetry of combination, and it's rather difficult to remember that. But if you want to have the full description of crystal and its symmetry, it is necessary to use a combination of theory of symmetry, and then you can use the formula of symmetry for giving this information. For example, this formula of symmetry means that there are 5 planes of symmetry. However, the theorem number 4, along axis of the fourth order, only 4 planes can pass. Consequently, the fifth plane should be different from these 4, and according to theorem number 2, if there is a center of symmetry, it should be perpendicular to the axis of fourth order. International symbols of symmetry classes are much more compact, and by the writing of a character we can establish the mutual arrangement of symmetry elements, of course if we know the theorem of combination. These symbols are not all written but basic, the so-called trasmente, elements of symmetry. The latest are referred as planes. The symbols of Hammond-Morgan are spread. Look here, please, and you can see the symbols in according of the Hammond-Morgan system. N is axis or inversion axis of symmetry of nth order. M is the plane of symmetry. Nm is the nth order symmetry axis and n symmetry planes passing along it. N divided M is an nth order symmetry axis and a symmetry plane perpendicular to it. N2 is the nth order symmetry axis and n axis of the second order perpendicular to it, in according to the theorem number 3. Mn divided mm is the symmetry axis of the nth order and the m plane parallel and perpendicular to it, and can take the values 1, 2, 3, 4, and 6. I remember you that there are no the order, the axis, or more the fifth order in the real crystals. When using Latin international symbols, one must always keep in mind the theorems on the combinations of operation. For example, symbol NM means that the plane M passes along the axis of the nth order. According to theorem number 4, there must be n such planes. The symbol n divided m is the only plane perpendicular to the n, but by the theorem number 2, it implies that if n is beside the axis of the plane, there is also a center of symmetry. When you write an international character, it is extremely important to comply with the order of record. These rules are contained in special tables. In the international symbols, there are distinguished the coordinate elements of symmetry passing along the coordinate planes, and the diagonal ones passing at the angles of bisectors between the planes. This is taken into account when writing a character. If it doesn't not comply, the meaning changes completely. Symbol M3, for example, means 4 axes along 3 bisectors of 3 coordinate planes of symmetry. According to theorem number 1, at the intersection of the planes there appear 3 axes of second order. By theorem number 2, at the intersection there is the center of symmetry.